Okay, so welcome to the oral session 5. So we will have 4 speakers, and the first one is the Zhuo from UCL, and let's welcome Zhuo for the first talk.
Shall I begin? Can you hear me?
Yes.
Okay, cool. So hi everyone, I'm Zhuo from Department of Stats of University College London. So it's an honor to give a talk at UAI 2023 here today. So what I'm going to present is meta-learning control rights, variance reduction with limited data. So this is a joint work with Chris Oates from Newcastle University and Turing Institute, and my supervisor FX Briol from UCL and Turing Institute. So suppose now we have a collection of T integration tasks, as shown in equation 1. Each of such integration tasks often consists of 2 components. So one target integrand, ft, and a target distribution pi-t. Furthermore, we will assume that we only have access to very limited data per task. The figure below shows an illustration example of such integration tasks, in which the black curves are the integrands of interest, and the counterplots are the distributions of interest. So this is actually quite common in stats and machine learning, from multi-fidelity modeling to marginalization problem of hyperparameters in Bayesian inference. So we will get more detailed example later. So in this case, how can we joint estimate those integrals? One common way is to use Monte Carlo estimators. That is, once we got NID samples from the distribution pi, we take the average of the evaluations of the integrand f at these samples to be an estimator. However, by the central limiting theorem, the convergence of this estimator to the true value is controlled by the variance of f, denoted by v pi f here. So this actually indicates that the Monte Carlo estimators often require a large number of samples and function evaluations to achieve good accuracy. So if we can construct estimators with reduced variance, then it is possible to have better estimators with the same number of samples and function evaluations. So one way to move forward is control rights, which is a powerful post-processing tool for Monte Carlo methods. That is, we can estimate pi f by pi f minus g plus pi g, where g is known as a control right. This is justified when we can find a function space, calligraphical g, such that for all functions g in this function space have tractable mean. And if the variance of f minus g is small, much smaller than the variance of f under distribution pi. This also means that we need to identify an effective control right from this function space. To find a function space calligraphical g, we can use sign operators. We can apply sign operator s pi onto some function u, such that the expectation of s pi u under the distribution pi is 0. Meanwhile, we can add a constant gamma to s pi u, such that the g gamma actually has mean gamma 0 under the distribution pi. Such function u can be neural networks, polynomials. So if we are using a neural network as function u, this is formally known as neural control rights. Oh, oops. Okay. Sorry. Okay, sorry. So now we need to select an effective control right g hat m from the above function space. So this actually can be done by minimizing the empirical variance of f minus g. So this is illustrated in equation 2. So the final step is, once we have identified the g hat m, we need to construct the control right estimator with the remaining m minus m samples. So this is shown in equation 3. In equation 3, we are actually using a Monte Carlo estimator of f minus g hat m, and then compensate this estimator with the mean of g hat m. So by the central limiting theorem, we know that the convergence rate of this estimator is controlled by the variance of f minus g hat m. So if g hat m is a good approximation of f, then that means the variance of f minus g hat m is very close to 0, and thus this gives us a faster convergence rate. However, the existing control rights methods still require a large number of samples to have good performance. And meanwhile, since they tackle these integrals individually, so they actually ignore the potential relationship among T integration tasks. So to the best of our knowledge, the only control right methods that learns and utilize the relationship among T-related integrals is vector-valued control rights. It reformulates the original problem in equation 1 into a vector-valued integration task. It derives metric-valued Stein kernel, capital K naught, such that for any function g in the RKHS induced by this kernel, has 0 mean element wisely for each target distribution. Though it exploits the shared information among integration tasks, it actually has a very expensive computational cost, which is between t to the power of 4 and t to the power of 6. So the key challenge remains to be solved is that how can we construct control rights at scale, sharing information across a large number of tasks, even with limited samples per task. So our answer to this challenge in brief is that we can reframe selecting effective control rights as optimization tasks and employ meta-learning to learn control rights fast and efficiently. So before going to the details, we will now have a brief overview of the proposed method. So for each integration task, we will split the data set dt into two disjoint data sets, st and qt. So in order to use Stein operators, we can find that the additional requirement is that we need to know the score of the samples. The proposed method actually consists of 2 steps. The first step is to learning a meta control right, while the second step is to obtain task-specific control rights from the meta control right. Intuitively, such meta control rights should work reasonably well for all integration tasks and close to most of control rights of integration tasks from the same environment. So cool, now we all have a good understanding of the proposed method. Now let's dive deeper into the details of the step 1 of our method, learning a meta control right. So we call that an idealized meta control right is a control right whose parameter gamma satisfies the following objective. Though this objective looks complex at the first glance, it is actually intuitively simple to understand. So the update step, marked in color blue, updates the parameters of the meta control right gamma with L steps, such that the resulting values of the parameters can lead to the minimized loss over all the integration tasks from the environment. Recall that here the loss is actually the empirical variance of the integrands minus a task-specific control right. This means we are identifying a meta control right whose parameters are close to all the other task-specific control rights on average. For instance, such an update can be L-step gradient descent with step size alpha. The above objective is hard to approximate, but luckily we can use gradient-based bi-level optimization proposed by Charles Finn. So that is, we can estimate the inner loss JT and the outer loss JT by JST and JQT respectively. So once being optimized, the resulting G gamma hat meta is the so-called meta control right. So the second step is now to obtain effective control right from the meta control right for each task. So which is referred as task specific control rights here. So this is actually very simple. Since we are using parametric functions and we can simply do gradient descent on the meta parameter gamma hat meta to obtain the parameters of a task specific control right by using the dataset ST of that task. The figure below here actually shows that how one gradient step from the meta control right can produce an effective control right for an integration task. The red dots here are the observations in the dataset ST, and the conditioning on this data, we do one step gradient descent on the parameters on the gamma of the meta control right, and which is marked in green. And this results in a better approximation to the integrand of this task, as shown by the blue curve. So once we got these task-specific control right for this task, we can construct a control right estimator as usual with the remaining n minus m samples of this task. So the first example I'm going to share with you today is the integration task of oscillatory function class. So consider the integrands of the following form with some parameters at. Know that the value of at corresponds to a target integrand. And this at actually controls the difficulty of these integration tasks. And in this example, all the target distributions considered is a uniform distribution on the random variable x. So the reason why we choose example is because we have tractable solution for these integration tasks. So in the left figure below, we are investigating the effect of number of samples per task with dimension d set to be 2. So we firstly learn a meta control right of each case, and then test the learned meta control right on 1,000 unseen testing integration tasks randomly sampled from the environment row. The blue curve here is actually the mean absolute errors of our method, and it always have the lowest error if being compared to that of control functionals and the neural control rights and the Monte Carlo estimators. So notably, the empirical computational cost of estimating control right estimator for these 1,000 tasks is about 6 seconds. So that's 20 times faster than neural control rights. In the right figure below, we are investigating the effect of the dimension d. So we learn the Meta-CVs for each value of d, and then test it on 1,000 unseen testing integration tasks from the same dimensions. So clearly, the curse of dimensionality is observed for all the methods, but our method still can have variance reduction when the dimension is smaller or equal to 5. The second example I'm going to share with you today is the marginalization in hierarchical Gaussian process. So while we assign priors to kernel hyperparameters x, and we need to integrate out the uncertainty of the posteriors of these kernel hyperparameters. And in this example, we actually taking a canonic example in the Gaussian process literature, which is Sarko's rubber arm. So, and here we are interested to estimate the Bayesian posterior predicted mean at an unseen state Z star. So if having a closer look at this quantity of interest, we can notice that the integrand of interest is actually the Gaussian process posterior mean of the response at the state Z star, given the values of the kernel hyperparameter x and the observations y1 to 1q. And the distribution of interest is the posterior of the kernel hyperparameters given the observations. So each state would correspond to a task, and we want to estimate the Bayesian posterior predicted mean for a large number of states. Meanwhile, this integrand can be very expensive to evaluate, as it takes q-cubic operations per evaluation. So making this example a very good illustration for the problems of this kind. In the figure below, we are comparing the performance of meta-control rights with control functionals, neural control rights, and Monte Carlo estimators. And meanwhile, investigate the effect of the number of updates L. So once again, we can find that meta-control rights tend to outperform all the other methods. And interestingly, we can see that there is a trade-off on the value of L by noticing that there is actually a V shape in the mean absolute errors when we increasing the value of L. As we increase the value of L, the task-specific control rights are less and less dependent on the meta-control rights, and that's the task used for training the meta-control right. So in practice, we would recommend splitting the task used for learning the meta-control rights into two parts, with the first part to learn the meta-control right, and the second part to tune the hyperparameters of the algorithm, such as the number of updates L. So we also established some theoretical analysis for the proposed method. The main theorem here established the conditions of learning meta-control rights successfully. B is the size of the meta batch. It is the number of tasks to update gamma per iteration. And ITR here is the total number of iterations to update the gamma. So this theorem is actually based on a press paper G et al. 2022 from Journal of Machine Learning Research. And these conditions are on the control right G as a function of gamma. For instance, it requires a G and the gradient of G with respect to gamma is bounded and Lipschitz. The theorem itself actually provide us insights into the practical side of learning the meta-control rights. For instance, the theoretical optimal meta step sizes and the optimal inner step size. However, due to the time limit, I will not discuss them in details right now. So in particular, for simple control rights, such as polynomial control rights, it is reasonable to assume that there exists a unique minimizer of the control right loss, which is the empirical variance of f minus g, and convexity around this point. So this leads to this corollary below. So it shows that the parameters of the optimized meta-control right is typically close to the minimizer of the task-specific objective functional. Now back to the first oscillatory example. So in this figure, we actually are investigating the effect of the meta batch size B and the total number of iterations ITR. So it is found empirically that a larger value of B helps to achieve the optimal performance faster, but a larger value of ITR results in improvement in performance as expected. So in conclusion, meta-control rights works well for variance reduction with limited data by sharing information among a large number of tasks. And it is scalable in the number of tasks T and the sample size NT per task. So if you find our paper interesting, you can see our paper for more theories and experiments. And thank you.
Thank you. Yeah, let's welcome the discussant Viplav for the discussion. Yeah, please. Oh, yeah,
Can you stop sharing, please?
Okay.
Hi. Yeah, thank you for the very nice talk and the very readable paper. I am Viplav from CISA in Italy, and I'm going to be the discussant of this paper. Just to briefly describe what the paper talked about, you wanted to estimate integrals which are associated integrals and densities using control variates under this kind of a formulation, and control variates were used for which approximate f using family of functions with known integral. So some of the key takeaways for me from this paper was that the method is applicable for a small number of samples and large T. So we all saw some great results on that. Seems like this is a very, very new problem, something that hasn't been investigated a lot. Then one thing I maybe was kind of missed in the talk was that these CVs, the control variates for new tasks can be computed at minimal cost because of this meta learning framework. You learn something, and then if you have a completely new task, there is no very little computational cost because you have everything existing in your model. So I think that was a really cool result. And then finally, Zhuo already talked about the potential specialization generalization trade-off as you increase the number of steps in the inner loop of the training. Yeah. So to talk about some of the other things, shortcomings or comments to the authors. So the first of all, the authors say for dimensions 3D greater than or equal to 4, the method seems to be worse than Monte Carlo, right? We saw that plot there, and I wouldn't say this is really curse of dimensionality. D4 is a rather small dimension, and I was wondering what the author has to say about this, because it seems like the other methods don't scale as poorly with the dimension as this newly proposed method. Secondly, I felt that throughout the introduction, the method was motivated through a lot of real-world applications, but eventually in the paper, in the results section, the focus was on very kind of toy real-world applications. Maybe this has something to do with the computational cost because neural CVs were used, and the cost is quadratic in the number of the parameters, and that's what I wanted to get a response from the speakers. Thank you.
Thank you. So I will answer the first shortcome. So actually, in our paper, we actually do the experiment for eight-dimensional case. So we have this Bayesian inference for the Lotka-Volterra system. So this is an eight-dimensional case, and our method still is better than Monte Carlo. I think this perhaps is more data dependent or the problem dependent. So it's not necessary that our method does not work when D is larger than 4, right? Well, the real world applications, I think that in the paper we have this Bayesian inference for the Lotka-Volterra system. So this is an 8-dimensional problem, and it also is very representative of real world problems such as ecology modeling and epidemiology modeling. So and also this Sarko's robot arm, I feel like they are already the real world applications. So rather than the toy examples, from my perspective. And I agree with you, the computational cost is quadratic in the number of parameters. And we actually discuss this challenge, this problem in our paper. And one potential solution is to use first order meta learning, or use hidden-free meta learning to alleviate the computational cost here. Yeah.
Thank you. Thank you very much.
Yeah, let's thank the speaker and the discussion again.
Thank you.